Okay, so we have about 30 minutes left to talk about this. And again, like I mentioned earlier, is that we will be talking about like neural networks over the next like 2 to maybe even 3 study groups. I try to combine 40, 41, 42 all together because I think it makes more sense to talk about it all together versus being like, oh, now we're going to talk about deep learning, because deep learning is just neural networks, but more neural networks essentially. It's not really anything too different. It gets more interesting when you talk about optimizations and stuff like this and different architectures and stuff, which we won't go completely into, but basically once you know neural networks, everything kind of just flows from there, and just in a lot of ways it's not really too different, but what you do with it becomes more interesting. I will tell you is that one thing you won't go into, because you can spend a whole lot of time on this, is things like sequence to sequence models. So, or sequence to, like basically anything with sequences. So recurrent neural networks, LSTMs, we won't talk too much about them, but I will talk about like how they work. A lot of that is because the inner structure of like, we'll see what neural networks look like, but basically a lot of the inner structure of that part is basically saying, okay, these parts will connect differently. But in the end, it's just basically the same thing as a neural network. It's just structured in a different way, okay? So I know you guys might not even know what neural networks are, so let's talk about that first, right? So, all right, so I'm gonna go through a little bit of like, I'm not gonna, this usually is a more interactive, I'm gonna kind of flow right through it, okay? So stop me if I'm going too fast or something doesn't make sense. So, all right, so let's hear what I have real quick. So you might have heard neural networks. I want you to kind of like, just kind of not stress out too much about being like, it's a neural network, you know, deep learning, does crazy stuff. I think sometimes the hype can kind of overshadow like you trying to learn it. But just know that basically there was this thing that was called a perceptron network. It was basically to model the idea of how neurons work. And basically the idea with neurons is that you have certain connections, and that these connections, our brain, some in our brain, are able to kind of process information and even store memory and stuff like this. And basically the idea came about, it's like, well, could we model this in a computer? And actually it's not too hard to model like an idea of a perceptron. And we'll talk about that. But note that this also came back in the 1950s, but it wasn't until really recently, and very recently, I mean like past like 10, 15 years, where we basically have a lot of data to actually feed our neural network. And we have the hardware to actually process all the data. So especially with GPUs and then now TPUs, we can actually process this information, and we actually get useful information before. Neural networks did exist, but they weren't that great because you just took a long time to actually train anything. Okay, so perceptron, what is this perceptron? So it's actually really simple. Basically, you have some inputs, you do some math, you basically do some function in here. So the usually circle represents kind of like some process, some function that's going on, and then we get an output. Essentially, that's all a perceptron really is. A really simple one basically would be one input, one output, right? So you can do some funky stuff to the input, output right here. And the idea here is that maybe these are connected to other perceptrons. So we can see an output here. Maybe each of these X1, X2, X3 actually come from a separate perceptron or 3 separate perceptrons and feeding in this information. So usually what we'll kind of denote this like is basically just with linear algebra. It's just like this X1, which is like the value of whatever this input's coming in, X2, X3, which is just value, like some number, and then multiplied it by what we call weights. So W1, W2, W3. So you can think of it on these arrows, like you can think of like how much does this this data point actually matter in the overall output. So you combine those together, and I'm kind of cheating. This is not 100% true. You would then combine them together and get an output. You might also use another function called an activation function or other methods in here to basically say like, okay, like, well, what does this really mean? So a classic example of this is like a neuron. Maybe neurons, for example, like I'm no neurologist, right? I don't know anything about neurobiology necessarily, but I'm told that the idea with neurons is that you might have like 5 neurons like kind of connecting to like one neuron, and it's waiting for a certain activation. If like enough neurons like fire, right, activate, then this will fire off signal too. So basically this output might be 0 or 1. Basically it's an all or nothing kind of deal. And we'll see that in our activation function with the sigmoid. For the record though, no one uses sigmoid for actual like training, but the idea is there where maybe a certain value, this has to hit a certain value before you say, oh, now the output has some significant value close to 1 versus 0. Okay, so that's basically a perceptron. Does that make sense to people? Basically, you got some inputs, you do some funky stuff in here, basically just summing them up together, maybe enclosing that whatever that value is that after you sum it with an activation, and then you get a new value out. That's all it is. Not too hard, right? Just linear algebra. So I'll give you a scenario like why this actually like means anything interesting. We can talk about like logic, right? And so let's do that again. Oh, I didn't run the function, just defining the function. So this is just for me to define the function, so I can use it later. So you know like logical operators, and and or, right? Give me a thumbs up if you guys know what I'm talking about, logical and or. All right, cool. So logical and or basically like this is a classic computer science, you know, mathematics like to talk about this. But basically it's that like, for example, and you basically can only have a true value if they're both true. And in computer science, and you notice in Python, we treat 1 as true, 0 as false. Technically Python can use like 2 as well, but we're just going to stick with 1s and 0s. So the idea here, denoted with this little up like caret, is and. So A and B equals C. So we're like, what does that mean? It's like, well, if A is true and B is true, then C is true as well. So we don't, that's 1, 1, 1, right? If A is true, but B is false, 0, then C should be false. Does that make sense? So we need both of A and B to be true in order to say C is true, or both to be 1 in order for C to be 1. So we see 1, 1, 1, 1, 0, right, should give us 0, 0 and 1, 0, and then 0 and 0 will give us 0. Basically, is that the only way you can get C to be 1 is if both A and B are 1. All right? Sound pretty good? Cool. So we can actually use the idea of a perceptron to actually like simulate this, actually calculate this part out. Because all we care about is like, okay, assuming we can only put 0s and 1s in as inputs, and we only expect an output as 0s and 1s, what can we do? Well, we have like x1, which is going to be our first input. Let's call that A, right? x2 being B, and we can multiply A, you know, I'll call it x1 from now on. We can multiply x1 by w1, some number, and then x2 by some number. And then we'll also have this B, which is, we'll call it the bias. Basically, it's just kind of like, it's usually by convention we have that in there. It's just, there's a few reasons why, but I won't go into it. But basically, we're going to keep this third part that's always going to be constant, which is always going to be 1. So essentially what we always have is something along the lines of, I'm just going to write this down here so we can see it. It's something like x1 times w1 plus, x2 times w2 plus 1, the bias, right? And that's going to equal something. And we want that only to be equal to 0 or 1, depending if we put 0, 1 for x1 and x2. Okay. Everyone follow me so far? Cool. So you can kind of see that, okay, I have this little code here to make it a little easier for us to kind of play around with. And the idea here is that we can change out w1, w2. We'll also say change out the bias. So I really should keep this as B, just because we could change B as well, right? And so we want to have this, we can have our weights and we can test it out and see, does it actually give us the expected C values? So note that basically 0 and 0 should give us false, 0 and 1 should give us false, 1 and 0 should give us false, and 1 and 1 should give us true. Okay, so it's not like an easy function. Like you can probably write an if statement pretty quickly, but we're using just pure mathematics to see if we can make this work, all right? So just to kind of give you an example, what if we just put everything as 0, right? W1 is 0, W2 is 0, bias is 0. Well, if we do that, right, that's going to be basically x1 times 0, 0. x2 times 0, 0, plus 0 is always going to give us 0, right? So it looks like it worked for most of the stuff, but you can probably guess is that the one thing that didn't work out is if they're both 1s. So if input 1 is 1, 1, the linear combination is 0. Don't worry about this activation output, but this is the output basically is also supposed to be, oh, what's going on here? What did I do wrong? Sorry. Victor, what did you do? This is not correct, right?
It is though, right? Because 1 and 1.
It should be 1 and 1, right? Should be correct, but the linear combination should be zeros. So apparently, past Victor messed up his function. I'm not going to debug it right now. I'm sad. I don't know what past Victor did. Oh well. All right, but this should basically, you can see the linear combination still works out. Like, let's pay attention to these parts. This should be 1, right? And we can see it's not. If I made this 1 right here, right? Then we can see, oh, that would work, right? This is 1 and it should be 1. I'm sorry. This is 1 and it should be 1, but it didn't work. Like, but these are all should be 0 and it's not working out correctly, right? So I want to ask you guys, has anyone got an idea of like what values you could put in for W1, W2? So you always get where 1 and 0, 0 and 1, and 0 and 0 always give 0, but 1 and 1 will give 1. You got some guesses? We don't have to take too much long because I do have a solution. So I'll try one out. I actually don't remember if this is right. So let's try 1 times 1 is either 1, right? Or 0, right? That kind of makes sense. So I'll put these both 1s and then say, okay, well, that means we have 1 times 1 plus 1 times 1. It's going to be this 2. I'm like, oh, it's off by 1. So let's say like a bias of like -1. So that way it corrects it. So that way, if we put 1 in for x1, 1 in for x2, we would get 1 on the output. We combine everything together. Okay. And I don't know if that's going to work out for necessarily for 0 and 0, but let's see. And you say, okay, we got 1 at the output, yay, and we got 0, hey. Ooh, didn't work out in this last one, right? But you can kind of see how you can play around with this. And it turns out if you figure this out, play around with it a little bit, here's a solution right here. So 0.5, 0.5, and -1. So eventually you play around with this, you can kind of get this. And gosh darn it, why is this not working in the way I think it is? I'm gonna see what I'm doing here. Well, let's just work this out mathematically, right? If this is 1, oh no, it shouldn't. Oh, sorry guys, I forgot. I added this in there later on. The function also has this activation. That's why it has this activation output. Basically, it checks it if it's less than 0, it's just gonna say that's 0. Like it's just gonna go for it. So that's the reason why it's actually able to do this activation output. So that's what's going on. But essentially what we can do is really quick mathematics to have something that's going to simulate something like a truth statement or like a logical and an or. Okay. Sorry, I should have reviewed this a little bit closer. Past Victor wrote this at some point and apparently he forgot what's going on. So, oh well. But the point is that we can actually combine this together to actually do some like mathematics with really simple structures. And that's really what a neural network is about. You can do the same thing with logical OR, but we're just going to skip over that. But if you're curious, you can do these different things, right? So this notebook's available for you guys to kind of play around with if you guys wanted to see what I was doing with my code and everything like that. But let's talk about neural networks itself. So, okay, that's Perceptron. So that motivates that whole idea that you can take something that's just structurally, basically just linear algebra, put it together. Key part's going to be that activation function, because that means it's going to help us make, we're always going to have either just 0 or 1 or some values in between. And that's really what a neural network is. So what we'll do is just combine multiple perceptrons together, and now we'll have this network, this neural network. So one way you can kind of think about this, this is kind of from the curriculum, is you can kind of think of these inputs like location, pricing, variety, and offering, right? So they're talking about like a house, like how much you are going to sell based on these different values, stuff like this. And these are our inputs. And you'll see that kind of like this extra, we call this like a hidden layer. Basically, it's another layer. Instead of going straight from location, pricing, variety, offering, straight to sales, what we're doing essentially, instead of having that 3-to-1 output, we're having these 3 inputs and basically some extra stuff happening out here, still getting 1 output. And the idea is that maybe it's some combination of these things. For example, let's say like location and pricing determine how many number of people that will walk by. So if you have a really good location and the price looks good, maybe something will like you'll have like how many people actually walk by. Affordability might depend on like just pricing and maybe a little bit of location. So the idea there is that these are kind of like latent features, kind of like when you talk about feature engineering, that's kind of what's going on here, but it's done more automatic. And I saw Jessica raise her hand for a second and then nod. Is that what you're going to say, Jessica?
That's literally what I was going to say. It's kind of like when we're feature engineering. Yeah.
Yes. So neural networks are really cool because they kind of do some feature engineering. Now, I will tell you in practice, it doesn't always do a great job of feature engineering. Like it sometimes just has a hard time to figure out what the right feature is. So I will just kind of go off a slight tangent. There's this problem called FizzBuzz in computer science. Give me a thumbs up if you guys are familiar with FizzBuzz. No? Hold on a second. I gotta close this door because this door is kind of opened up. I'm back. Sorry, my door opened up and there's a dog barking. So FizzBuzz, basically, it's a kind of a computer science problem. You can think about how to do this. Is that if you have a number, you take a number, and if it's divisible by 3, you say fizz. If it's divisible by 5, you say buzz. If it's divisible by 3 in 5, you say FizzBuzz. Otherwise, you just say the number. So it's kind of like a classic game. You just go, okay, 1, 2, fizz, 4, buzz, fizz, right, because 6 is divisible by 2, and then 7, 8, fizz again, right, and you would kind of go through, and then you get to 15, you say fizz buzz. So the idea is like you could kind of write a program like, how would you do this, right? It's a classic problem. Someone actually said, let me see if I can do a neural network, like write a neural network to do a fizz buzz. And it technically did it, but it did it in some weird way. Basically, it ended up finding features that, like, what's the best features for this? Like, if you have a number, what feature would you want to know about it? Is it divisible by 3? Is it divisible by 5? Problem solved, right? Like, basically, that's the only features you really care about, right? But the neural network doesn't know. It just knows inputs and outputs, right? And so having hidden layers enabled it to basically try to figure out feature engineering, but it basically ended up, I can't remember the exact details, it figured out how to find if a number is divisible by 24 and if it's divisible by like 50 or something like that. And those features kind of worked for some numbers, but sometimes it didn't quite work out. So neural networks don't always know what the best feature is. It just knows a good enough based on cost. And sometimes it's just going to mess up in the sense that it's just always going to have, it's not going to find the best feature, right? And it might also take a long time for it to figure out what that feature is. Okay, does that make sense, people? I don't know. Anyway, you can think of like neural networks as basically like these deep hidden layers just trying to find latent features. And the way these kind of work is that we have different weights, right? Different values on these arrows. So like maybe location matters more for affordability, right? So maybe this value is like 10, right? Versus like variety and offerings, like doesn't matter, or in fact it's like the opposite. It's like, oh, if it's too varied, maybe the affordability is just out of whack, so it's like minus 100 or something like that, right? So you have different weights and stuff like this to make these new like latent features. We call this the hidden network or hidden layer. Okay, so I'm kind of just going through this a little bit because it's more curriculum, like you guys can read this through, but basically we can formalize this into saying like, okay, we can actually have this equation written out. Like for example, z equals w1 times x1 plus w2 times x2 plus b, right? So basically we have all these inputs, which I don't really like. This is from the curriculum. I don't really like this. I feel like x1, w1 really should be tied together, but you can kind of think like, oh, these inputs are put together to feed into get this z. This is classically what you see it written as, is z. And then it's like, okay, z, and then we have, well, we want to have our last output, but we'll actually have an activation function. That's what the sigma is representing. And y hat, what does y hat represent when we say y hat in, when we talk about machine learning models?
Y predicted.
You're predicted, you're right. So y hat is our predicted value. So our predicted value is basically sigma of z. Basically, this activation to basically, you can kind of think of it like it turns it down or turns it up, right? So it's kind of like the gatekeeper of like what's going on. We'll talk more about activation functions over the next couple study groups. But the idea here is like we have the activation function, we have our y predicted, and then we have this funky guy here. So you look at this curly L with
the loss
y.
function.
Yeah, the loss function. So this curly L, the y hat, and y. So remember, y is what the actual value is, and y hat is our predicted value. So the loss function basically says, hey, how well did you do? Did you do well? Did you do badly? And that loss function here can be defined in different ways and stuff like this. That's actually really cool stuff. Note that loss function is related to our cost function. If you guys remember back to gradient descent, back in what, like mod 2, maybe mod 3? It's been a while, right? But our our cost function is related to that loss function, basically. It's like how far off are we from our predicted or our true value, our true y, okay? And that's gonna be the holy grail of neural networks. Say, hey, like, how do we know what W1 and W2 should be and B should be? It's like, well, what if we just minimize this loss? Like, what if we just say, well, how can we make that loss as small as possible? Can we make y hat and y very, very close by adjusting W1, W2, and B? Now imagine, like, this is why I kind of give this problem out here. If you try to manually do this with however many parameters, right? You can imagine you'd be here all day. Like, think whatever values you can do and try to adjust it all day until you get the right value for not just one instance, but like I had 4 examples and you can see how long it could take for you to figure it out. Imagine you have thousands and thousands of examples, or maybe millions of examples, and trying to find out the right parameters, the right W1s, the W2s, W535, figuring out what to tune it to make sure this y hat are very close together. Really tough. So we use gradient descent to basically what we call propagate that error backwards, or back propagation, propagate it backwards to figure out, as we kind of say, okay, well, this is how far off we were. what if we adjust it by this much, and then we adjust it by this much, and this much, and this much, and going all the way backwards. And that's going to be back propagation. I saw a hand go up. Yes, yeah.
Yeah. Okay, so this equation looks like linear regression.
Mm-hmm.
So do we ever have like polynomials?
So that's a good question. It's like, oh, like, could we use polynomial? And the answer is almost never. And the reason why is because it's honestly too complicated. Like, it's just, I shouldn't say it's too complicated. You could technically do it, but it's not necessary, because what we trade off with this, like, we could make this more complicated. What we do instead, we make the structure more complicated.
I think
That makes sense.
I think in the back.
Oh, someone said it. Okay.
If you look closely, what you really got right is linear regression,
Mm-hmm.
right? Because when you put a linear function through a nonlinear function, you're basically doing linear regression, aren't you?
Mm-hmm. That's essentially what's going on here. It's linear regression, but because we're going to end up having multiple layers, it's like you're having linear regression on, like, if you look at just, I wish I was covering my hand up, you guys can't see that. If you cover up these first inputs and look at just like these latent features, it's like you're doing a linear regression on just these latent features. The thing is that these neural networks can literally be like many, many layers deep, where what exactly, by the time you get to here, like, what exactly are those features? And it's kind of hard to tell exactly what's going on because it's done automatically. But essentially what is like, oh, you could take these features and actually do linear regression with it. And we can talk about this in transfer learning. That's kind of what transfer learning does. Like, hey, let's figure out a neural network that does really, really well in this problem, get those latent features and use those latent features to do our real problem. Like, that's kind of like the idea of transfer learning. But the reason why, like, Jessica, you were kind of going back to say, why could we use polynomial and stuff like that? You technically could, but in a lot of ways that's feature engineering, if that makes sense. So if, let's say, x squared was like a really, like, oh, we really should have x squared in there. Well, what you might actually have is that you might have then this feature kind of emphasized, and the neural network might try to go towards something that's like x squared. So it might try to double count x1 multiple times. Another solution to this is that's like, oh, if you feel x squared should be in there, you just have that as one of your inputs. It's like not just x1, but also x1 squared. And that's a feature you put in there. And sometimes that will emphasize, or not emphasize, encourage the neural network to move in the right direction quicker versus it trying to figure it out. In fact, we will see this a little bit. I'm going to skip over real quick because I think that's opened up a really good point. There's this little playground here. I'll share it in the chat because I think it's fun. I don't know if anyone's seen this before. Where's the chat? There it is. So I know we're a little bit over time, but I think it's worth kind of going through here. So we're basically in the end just doing machine learning to the classification. Let's say, okay, let's separate the orange points from the blue points, right? And we'll just start with this guy right here. And this is kind of fun, is that you can have x1 and x2. So those are your only 2 points, basically, or inputs, is either x1 or x2. And essentially we have our neural network here. This is kind of like pretty much what we're seeing right here, right? You can kind of see that similarity. Essentially, these connections are going through, and then we're gonna have some outputs right here. We'll get rid of this hidden layer just to make it easy. And you say, okay, x1 and x2 are going to combine into these latent features, whatever this is, and it's going to output. And then what's going to say, okay, there's going to be some loss, and we're going to adjust that loss. Like, we're saying, oh, we're off by this much, so we're going to propagate the error backwards, adjust how much these weights are. So you see this weight's 0.38, 0.28, you know, so on. You can even change this. And what we're going to do, we're going to automatically go back and forth, essentially, of saying, like, okay, here's our loss. You know, let's propagate this backwards. Update these weights, and try again. Feed it forward. Basically, we feed the data through here. That's what's called feed forward. We'll feed it through here. We'll see what our new loss is. Like, oh, then do where we go. All right, we're gonna propagate that error backwards and forward, backward and forward, and backward and forward. This process of going forward and then backwards is called an epoch or an epoch. So you'll hear me call it epoch a lot, just because I don't know where I learned epoch first, but it definitely was someone probably who wasn't from the US necessarily. So that's why I always remember it as an epoch, but you'll hear people say epic a lot. I think either pronunciation is fine. But you'll see this epoch basically going back and forth. And what's kind of cool, we can actually see it get better and better. So if you actually look at this test loss or even the training loss, you should see this go smaller and smaller. And I can actually go one epoch smaller and smaller. And you can see Sometimes you do better, sometimes you do worse. And you can see here, this is the visualization of what's going on. It's predicting that this blue shaded area is blue. Sometimes it's making mistakes like this orange points. Sometimes it's doing pretty well. And basically you can see these weights, these adjust over time. Now, what's really fun is that you can just press play and you can see these weights change over time. And you can see it kind of fluctuate to here. Now, let's just say you had something really complicated like this, and you try to rerun it, right? Well, you can probably guess is that these weights are going to try their best, but maybe this is just never going to get there, right? So maybe, for example, like this really cool, like Jessica was saying, we could have polynomial. It's like, well, you just treat that as a feature, right? So now we have a new feature in here, that's this part. And these are basically combining all together to make latent features, okay? And so you can kind of see a little bit these weights changing. You can see the thickness change based on like what the weight is, right? And you can kind of see a little bit, and you can see this neural network is trying its darndest, right? It is trying so hard, and it just wants to get it right, and it's just not getting it right. And so one thing you can do with neural networks, and I'll show you one strategy, is essentially make it more complicated. You can add more layers. So like think latent features, making new latent features to make new latent features to make new latent features. Complicated, right? So the thing about this is that it just means it takes a lot more time, it gets more complex, but with that complexity, it hopefully is able to get a little bit better. And you can still see it takes a long time for us to get even close to something that seems reasonable. And you can see it's gonna kind of stagnate here, and maybe it's never gonna do any better than that. So this is one strategy you can do. And in fact, you can put a lot of parts in here, but maybe all it takes is having the right feature, right? And I'll put in like these other ones. So this is just x1 times x2, kind of like think of like polynomial regression, right? Like kind of adding those in there. But instead of having it like connected here where like, oh, x1 and x2 combined, we're just putting it in as an input feature. And same thing as sine x1, x2. And you can probably guess as we get these parts, and I'm gonna just make this really small just to kind of show you. And remember, I think we got like 0.2 something was the training loss. If I run this now, we'll probably see this training loss. I'm assuming it's gonna get a little bit better. And it's still having a hard time, so maybe we need to add more layers and stuff or just give it more time. But you can see it's getting better and better, but it's kind of overfitting, right? You can kind of see it's like, it's trying, but it's like, that's not quite right, neural network. You're just not quite there. So this is where like extra complexity can go through. And maybe, you know, you can play around with this different stuff, like for example, different activation functions or regularizations and stuff to help it from overfitting. So you can do a whole lot of stuff just to visualize this, but you can see, I think this is a great example. This actually ended up doing maybe a little bit better, but it took a while for it to get there. And even at the end of the day, if I pause this, kind of like a spiral, but it didn't quite get it right. It's only going to do as well as it learns from the data itself. So this is what our next like set of like, you know, study groups are going to talk about. It's like, okay, once we have the structure, which actually isn't too hard to like build up, how do we make it learn? You know, we call it learning. Like, how do we make it get to what it needs to be? And basically, how do we know how many hidden layers we are, and what the activation is and stuff? And to be quite honest, it's not always straightforward. In fact, in a lot of ways, it's very mysterious and like exactly how to make this work. There's a lot of given research, but that's kind of what we're going to talk about. It's like, okay, what activations to look for? What kind of things as a data scientist or a machine learning engineer? It's like, what things are you looking for to make this work properly, or at least to get to a closer answer? And this is why I will tell you, we talk about neural networks and deep learning, when deep learning really relies on neural networks, it's not always the solution. And this is where like a simple linear regression can actually give you plenty of great, you know, solutions without ever having to touch any deep learning stuff. But those really complex problems, the ones that are hard to like quantify, so think of like image recognition, it's really hard to tell like what in this picture of a cat makes this picture a cat versus a dog, right? And it's like you kind of instinctively understand, but like how do you quantify that? And then think of all the pictures of dogs, all the pictures of cats, and including that in like your specific definition of what you're looking for. And that's really tough to do. And that's where neural networks, deep learning does a really good job, because we can basically say, well, we don't know. We're going to abstract it and let you, neural network, I'm obviously anthropomorphizing, right? Like it's not real, but like, not real, not really alive, but like we're going to have you figure it out, and you're going to figure out how to do this. So it's kind of interesting because it's very opposite if you're used to regular programming, where you essentially are saying in programming, if this happens, do this. If this is true, do this. If this is this, do this. Where the neural network says, all right, here's our inputs. This is kind of machine learning in general. Here's inputs, here's our outputs. You figure out how to connect these things. And when we say you figure it out, we have to encourage it, like how you would teach a child, right? You don't just like teach a child by just like to walk, but just like putting the child on the ground and say, all right, walk, right? Like, well, you might kind of pick them up a little bit, you know, kind of encourage like, all right, see, this is how we use our legs. And then say, okay, like when they start kind of trying to stand up and they stumble, like, yay, good job. Like, you're doing great. You know, you didn't quite get it, but you're almost there, right? And eventually with encouragement and the proper encouragement, eventually the child learns to walk. And that's just like our neural network. You know, it's just learning how to walk and trying to figure it out. And it's just trying its darndest. Look at it. It's not there, but it's got the idea. And that's what we're going to do as data scientists. Basically, data scientists are parents. So, cool. Anyway, I know I'm kind of going over. I know I kind of went away from the notebook itself, but I think that's okay. We will kind of go through the different parts. So I kind of already went through a whole bunch like layers, weights, activations. I kind of mentioned this a little bit. We'll talk about hyperparameters, which are kind of, why are they called hyperparameters? They're parameters that basically affect the learning versus like the actual code of it, if that makes sense. So that'll be interesting to talk about. And then we'll talk about actually training it, like what the heck is going on in here? Like, why is this working? Okay, so we'll talk about that with the actual training a neural network. So when a neural network learns, we talk about training it, just like we got the train test split. And then we can talk about a little bit like bringing that complexity, like having multiple hidden layers. So we'll talk about this next time. Your homework for next time, right, is to make sure to go through section 40. I think that will be helpful to see the mathematics. I'm also going to send out a video, and I see Kayla's here too, but I'll put it in, I'll put on the Slack channel. I'll also put it in the video description. That way you guys can find it if you guys are watching the recordings and stuff and like, what is this video? I think some people have already seen it. I know I've already seen it. Is 3 Blue 1 Brown's description of neural networks. I think he does one of the best jobs of visually showing what a neural network is and also mathematically talking about it in something that feels digestible. It's probably like, it's a set of videos. It's got to be less than an hour, like total. And I would say, you know, an hour of like watching a video. Don't feel like you have to know everything about it watching it, but just, I think just watching at least the first couple of videos in that playlist I'm going to send out is going to be more helpful, like just to visually see it. And I honestly, I wish I would say like, I wish you could just like learn everything from me. And like, I'm a great teacher and I just distill knowledge, but I know that's not true. That's not how teaching works. So I encourage you guys to play around with it and see different sources and see different people talk about it and see how this works. Because it's kind of complicated, but once you kind of get the idea of it, it becomes a lot more digestible and understandable. And from there, it's just a stepping stone to figure out all these other deep learning network architectures.
It's all about the chain rule.
Yeah, chain rule. Yeah, you see, this is the whole point of calculus. It's just so we can figure out how to do neural networks. But that's essentially what backpropagation is, basically because it relies on the other one. And I think 3 Blue 1 Brown does a great job explaining about this like chain rule, backpropagation, and neural networks all together. And honestly, I don't think I found anything better that does a visual sense with still mixing in the mathematics without getting metaphysical or glossing over too much, but with also not like rely in the sense that you have to be a mathematics major dug deep into the mathematical notation and understanding exactly what's going on. 3 Blue 1 Brown on YouTube does a really great job of doing kind of putting a little bit of both of those things. And it's just soothing. It's got pretty animation at the very least. So that's your homework for next time. I will make sure to share it out to the Slack channel. I'll put in the description video for the recording. That way, in case if anyone from the cohort, anyone's like looking at this later on, like, what's this video? We'll have it in there too. But before we head off, I know I was kind of went a little bit over. Are there any quick questions or anything you guys would like to ask or clarify before we head out? Yeah, pretty good. All right, so I will stop the recording here.